If you don't have the patience to sit through a video like this, and you don't have the patience to quadruple check everything that you intend on plugging in, you don't have the patience to see a build like this all the way through properly. By the way, pro tip, if you are making a charge adapter or just soldering wires into an XLR plug, specifically the female end, first thing I like to do is to get the corresponding male end and plug it into there. This is the core of it that you're soldering the wires into. It holds the barrels in place since they're sitting in a plastic holder mold. And when that heats up, the plastic melts and the barrels can actually become off in terms of their position. Having it sitting on the mating plug and holding that keeps them from going out of alignment. Also, these cups, you can fill them. I would, because what happens is when you have the wire going into the solder cups and you fill it with solder, you have more actual material for conductivity going from the wire through the connected pins rather than having a gap where the current flows around the outside of an empty barrel. And so those are just two things that I think help, and I think they're worth mentioning. Hello everyone. In this video, I'm just going to walk through how I set up this. This is an ENNOID XLITE V1 Smart BMS, and it is going to be set up with my battery for the VESC one wheel build project. And this is a 20S 2P battery pack. And what I've got in front of me is with the least amount of specialized tools that I can do this with, and that is the battery, the BMS, a multimeter, the charger, the wall charger, which terminates in an XT60 male for some reason, and then an adapter I soldered together that goes from the XT60 to the XLR, which is the charge port that is on the controller box. Now, if you have none of these, especially a multimeter, and you cannot solder an adapter like this, I would very much walk it all the way back and do a whole lot more reading, learning, and practicing. Because a project like this, even something that just involves software with configuring a BMS, this is not a good first project. If you don't know how to measure polarity or check polarity, and that is entirely foreign and alien to you, if knowing what the voltage of a 20S battery is and being able to internalize and memorize that, if that is still something that's very far off in the future for your DIY project journey, this is not for you. That might not be the nicest thing to hear, or it might not be what you want to hear, but mishandled, these things are dangerous, period. If you get the polarity of something wrong and you plug it in, whether it's the wall charger into something else or it's your battery into something, and the polarity is reversed, something will blow up. Something will explode. I don't know the magnitude of said explosion. It could be a component in a circuit board, whether it's the BMS or the ESC, popping, and then there's a hole in your PCB, or it could be something exploding in the charger. It will blow up in one way or another. And so if even the idea of checking polarity is way far off for your particular learning journey, just stop. Just don't. Don't do it. I would rather, refund people for a battery they ordered and have people be upset at me than have people create dangerous situations for themselves, because that is bad. Stuff blowing up is bad. Expensive circuit board parts blowing up and your money just burning away and you getting hurt. These are all bad things, especially the getting hurt part. Sometimes you get the polarity wrong and then it blows up while it's in your hand, and that kind of injury is really bad. Heaven forbid you do something wrong with the polarity coming from a battery, and then the battery gets damaged, and then that starts going wrong. These are situations that you just don't want in your life. I don't want them in mine. And so if this is the sort of thing that is far outside of your scope, and it's all foreign and alien to you, just stop. By the way, if you were one of the people that ordered one of these 20S 2P XR battery box batteries from me, do check your email inboxes. I will have sent 2 emails by now. one regarding the BMS situation and availability, and another that needs to be responded to before your particular order ships out. And so do check your email and reply to those as soon as possible. If you have already, just ignore this. Now, how I normally configure these BMSs is, of course, with the multimeter, but not with the charger. I use a power supply over there, and I hook that up directly to the charge input of the BMS, and I use this just to connect directly to it. What that does is, since that power supply has a panel on it, I know what current it is set to, and so I know what current is being charged to, and that is something you need to know in order to adjust one of the parameters on this to make sure that the current being detected by the BMS is accurate to what it actually is as far as that instrument panel goes. And that can also be checked with a multimeter. You can measure current flow with a multimeter, which is why I have these wires exposed, because we're going to use that. I'll explain that in a moment, but ideally you would use a power supply that can apply 84 volts to a 20S battery or whatever voltage is appropriate for the series count of your battery, and you would be able to just see on the panel what current you are using to charge the battery. If you want such a power supply, which I do recommend, I will link to the one that I got recently in the description below, because it replaced another one that burnt out, and so that one's relatively new. It works decently, and I've had no trouble with it. Now, starting with the multimeter, which is necessary for everything, this particular one has probe covers for the measuring probes, which do come off, and you want to either keep them on or remove them depending on the situation. Sometimes to measure something, you got to get the full probe in there, which is the case for this. Now, this charger is plugged in, and it has a male XT60, and you don't really want to measure male connectors, because what you have to do is touch a probe to each one and hold it so steady that they don't touch each other and cause a short circuit, and that's bad. It's much easier generally to measure the female connector because the barrels are naturally separated. And so in this case, this shipped with this male connector, and so I made this adapter with a female XT60 going to the XLR. And the most common polarity that I've seen is that pin 1 is positive, pin 2 is negative. That's not the case on regular Future Motion 1 wheels. That is not the case on regular Future Motion 1 wheels. So, measuring polarity or checking polarity is important, and that's what we're going to do. Now, checking polarity only actually matters if you know how you wired your stuff. So, the controller box, and this is the one that appeared in a previous video and was in a build article. I know how this is wired, because this is relatively transparent and you can kind of see red and black wires, but also I made sure to take pictures and note where the wires went. And so I know that on the charge port, since this has, if you look all the way in, pin markings 1, 2, and 3, pin 1 is red and pin 1 is positive. And so I know where it goes on here. And so I know that pin 1 is red and therefore it's positive, and that it goes right there. So it's 4 in on the top. That might not be how you wired your box. That might not be how it is in your situation, but you need to know where your wires go, and you need to know what polarity is what. So red is positive, black is negative. In this case, pin 1 is positive, pin 2 is negative. In this box, the charge port, pin 1 is positive, pin 2 is negative. If this is all obvious to you, great. But I want to make sure that this has the proper polarity, and so we set it to measure DC voltage. And you'll notice you got the numbers, and this, even though I'm not measuring anything, there's a little dash. That's a negative, all right? And so if it's measuring negative volts, that means the polarity is reversed. So pin 1 here is on the right. Stick the positive in there. Stick the negative in here. And it will measure the output of the charger, which is 84 volts, which is good because that's 20S, 20 cells in series. And there is no negative marking. So that means that the positive is where it should be and the negative is where it should be. So this is the expected polarity. Positive is indeed on pin 1, negative is indeed on pin 2. If we reverse it and put the positive where the negative is and the negative where the positive is, it will read 84 volts, but it's reading negative 84 volts. And so that means that if I connect the positive here to pin 2, the polarity will reverse, or will be reversed, and it'll just blow up. What blows up? Who knows? Why would you want to find out? And so now that we know that the polarity of this is as it's expected for this particular device and layout and charger, polarity is positive on pin 1, negative on pin 2. I know that these pins correspond to that. I know that my positive red is hooked up to pin 1, and this is pin 2, which is the negative, the black, and I know where it's going here. Now that the polarity of the charger has been checked and I know where the wiring is going in the controller box, it's a good idea to make sure that your particular wire harness is also set up properly. And this stuff that I've been talking about so far doesn't just apply to the ENNOID XLITE, it applies to the ZBMS and any other charge-only, or frankly any BMS that you're going to use, or anything at all to do with connecting DC power sources. You need to be able to remember, make note of, and trace whatever wiring it is you've done or are going to use. And so I've checked the polarity of my charger and the XLR adapter. I've checked and know the wiring for the charge port into the Molex connector pins here. And so I know where they go. I've been able to trace them. I made this harness myself, and so I will have a link to the photo and the build log of this particular harness. And this harness is made to work with how I wired the charge port specifically for a charge-only BMS. What that means is that this charge port that I'm going to plug the wall charger into when this is all done has its own separate circuit that connects only from this charge port to these pins for the harness, and they're separate wires, their own wires that go into the box through the wiring harness and end here. So that means that this little XT30, that's what this plug is, this XT30, the only thing it's connected to is that charge port. The thing that the wall charger plugs into is right here. That's it. This touches nothing else. It does not touch the terminals of the battery. It does not touch the ESC, the little Fokker that's in here. This is an isolated, separate, distinct charge line, positive and negative, red and black. This goes all the way through here, knowing where the pins go, traces all the way to the charge port, which means that the positive from there touches the positive pin on the charge port, goes to the positive pin here through this red wire, and ends right here. That's all it does. And again, you have to be able to trace that stuff. If you don't and you plug it in wrong, stuff will explode. And that's important to mention, even if you know it, because at least then I said it. And the reason I'm making such a brouhaha about this polarity and tracing your wires thing is that I can never assume that any given person knows a certain amount of things. It's more common than one would think for someone to see a 20S battery of an 84 volt charge voltage and then ask if they can use their stock one-wheel XR charger with it, even though that charger outputs 63 volts for a 15S battery. There's nothing wrong with not knowing these things. However, there are certain things that if you get wrong are very dangerous. Once you learn them and you are familiar with them, the danger is very, very low and the risk is relatively low. However, not knowing these things and not being able to check your work and verify someone else's work does create dangerous situations. And so I'd rather have people be bored with a long video explaining things than hurt themselves and damage their property. So anyway, the stock Maker's PEV setup that they offer as a drop-in conversion for a one-wheel XR conversion kit, which is, the complete box that plugs into the existing stuff, that's not usable with a charge-only BMS, which is what this is wired to go with, and what this and the ZBMS are. So this is wired in such a way that the discharge going into the little Fokker in here is direct from the battery terminals, and the charge circuit funnels through a separate wire, charge-only BMS. The stock one-wheel XR stuff and the wiring that's one path to the battery and back is different. This needs a separate charge circuit, which is how I've wired this, and it's how I logged it in the build article. So there you go. Now, the battery does sit in this box. This is not the final installation of this. Before this gets all wired in, plugged in, and closed up, I will be using some cushioning foam underneath it and around the sides just to make sure that it doesn't move or jostle, because this thing is a pretty good fit and there's like a millimeter or two of wiggle room, and that's good for the wiring, and you just want to make sure that this gets padded. So if you did order one of these, I will toss in a sheet of this foam because this is what I use, and it works well, and it cushions, and it molds really nicely, and once you got it in there, it'll prevent that wiggle. Another note, the XLITE is a CAN-enabled BMS. Depending on how you want to use it and how you've wired up your harness, you may want to use the CAN, which is Controller Area Network, function to have this communicate with the little Fokker. If you do that, the CAN bus connector, which is this one, and you should be reading your pinout, that you may or may not have wired into your wiring harness, should be the absolute last thing that you ever plug in, period. Now you'll notice that I actually have the Molex connector plugged in already. And the way I'm going to do it, and the way I think is a decent idea of doing it, is that this gets plugged in, then you do all the wiring in here, and you close it, and then this stays together, and that's it. If you mess up the connection order, and you have CAN connected with the enable and ground pins, and then that gets connected in the wrong order, and then the grounding for the battery and the ESC are connected in the wrong way, you will burn out the CAN controller chip on this BMS. So the way I have it hooked up is slightly different than, now the way I have it hooked up is in the following way, which again is explained in the log for how I made this wiring harness. I have the discharge connector, which is this, the XT90, and this is the power that goes into the little Fokker. That's what powers it. Then I have the wire coming directly from the charge port, which goes into the BMS to charge the battery. And then I have the CAN wires here. However, it is only the CAN data wires, CAN high and CAN low. It's two wires that go to two of these pins. The reason I have it that way is because I would like for there to be some CAN connectivity with data going to the VESC while it's plugged in and charging. Because when this is charging, the BMS wakes up and manages charging. When it is no longer charging, it times itself out and shuts down, because this doesn't need to be awake for this to work with the little Fokker. The VESC will draw power from the battery independent of the BMS because it's direct. This is charge only. And so this doesn't need to be awake while the device is in use. It wakes up when you plug it into charge. And so when it's charging, it will send data to the VESC, and that's fine for me. That way I can check the voltage levels and the battery condition while it's charging, because it will be awake and it will transmit data. Then when I unplug it, this will go back to sleep, and then I can use it normally. That is how I have it set up here. It will be explained more in the log for this wiring. You may choose to do it differently. If that's the case, either way, make sure that the CAN connector is the last thing you connect, and all power should be connected and secured before a CAN is connected and you close it up. And that is how I'm going to do it. This is connected. This will all be connected, secured, and secured in the battery box, and then it will be closed and installed into the rails as is. If for some reason you need to disconnect this and then you want to reconnect it with the Molex, what you probably should do is open this back up, disconnect the CAN wire, then connect the power, then connect the CAN wire again and close it back up. The CAN wiring should be the last thing you plug in. Now what I'm going to do is kind of in contradiction to what I said earlier, that you don't really want to measure with a meter and probes on a male connector, because the pins create a situation where you can easily short them, because there's nothing blocking them like it would be in a female plug where the barrels are inherently separate. However, in this case, what I have done here, and this is the only way that I would personally do it, is I have the probe covers which only expose a slight bit of the probe, and so that will help to prevent slipping and shorting. Ideally, what I would do is this. And in fact, I'm going to go ahead and do that. I'm going to take my helping hands setup, which has an alligator clip, and I will clip this in place. So that way I don't have to worry about this thing wiggling. It's going to be relatively solid and it will be right there. And so what I'm going to do is triple check, quadruple check. When it comes to polarity, triple, quadruple, quintuple, sextuple, septuple, octuple. I don't know any more than that. Check over and over polarity before you plug stuff in, okay? And again, if this is really, really foreign and alien to you, just stop and have someone who's competent and qualified help you. Because this is 84 volts, this charger is 84 volts, this is a lithium-ion battery that, if mishandled, is dangerous. So don't fuck around with this shit if you don't know what you're doing. That being said, here's how I'm going to check polarity, just to make sure that when I plug this into the BMS, it's not going to blow up. So we have the charger plugged in to the outlet, the adapter. So this is the charging setup, XLR connector, which is going to go into the charge port. And I will connect it to my charge port. So it is connected to the charge port. And the charge port is connected to the wiring harness. Like I said earlier, I've traced these wires, and so I know where they go. And so I know that my charge connector, which is this, which is going to go into my BMS, I already know, because I know where the red wire is, what the positive is. However, I am going to triple check. And this, since this is a male connector with pins, I have to be dead careful. Dead careful. So these barrels have little nibs in them, and they're convenient because you can shove the probe right in there and it kind of sticks, because these pins have 4 little fins in them that create the barrel shape. And so I will prop this up so it is easy to view, and my expectation is to see 84 volts with no minus, meaning that I know where the positive and negative are. So I'm going to place that there, very carefully, place that there, and you don't need a lot of pressure because you're just checking voltage, and the meter should register. See how I'm slipping because I'm looking at the camera? You don't want to do that stuff. 84 volts, no negative symbol, all right? If I switch it and put the black probe where the red wire is, and vice versa, I will see 84 volts with the negative symbol. So that means that this, connected through the wiring harness, charge port, all that stuff, is the correct polarity, because the positive is measuring where it should, and the negative is measuring where it should. All right, so while I'm adjusting this, I'm just gonna zoom out and move some stuff around. I'm telling you, if you plug something in backwards with reverse polarity, you are going to pray that all that happens is that you just sunk hundreds of dollars worth of stuff, and that's all. Because you wind the clock back a couple of years, and I did some nonsense, and I got hurt. I'm talking burns and broken skin that took a very long time to heal properly, and that is not something that you want. That's not something that I want to happen to anybody. And at the very, very worst, you're risking electrical damage to a battery or a charger, and these are not situations that you want in your life. And so quadruple checking something that you are absolutely sure of is key before plugging stuff in. If you don't have the patience to sit through a video like this, and you don't have the patience to quadruple check everything that you intend on plugging in, you don't have the patience to see a build like this all the way through properly. Now, for the XLITE, it is said that the connection order between the pack terminals and the balance wires don't matter. I don't know if it does. I've done them both ways, and this apparently has a smart enough integrated circuit that it can manage that. This particular one, I have used conformal coating on the back because when this thing has like 84 volts in it, and I've pressed in a connector and had like the back of the stuff just poke my finger, I've gotten bitten before, and so I conformal coat the back, and that's good. So that's what that is. I will now connect the pack terminal, which I know is the correct polarity because it is wired as such from the battery. So this is the plug from the battery. This is the first set of balance wires, which is the larger connector. and the light will go on, and then we'll do this one. And so there you go. Now the BMS is itself connected, and so what we will now do is connect the charge port. So this is from the wiring harness that's connected to the charge port over there, and this is just a very rough fitting for the sake of configuring the BMS. This is not how the wiring is supposed to look when it's all going to be closed up, and so this is a rough plugging in just to get everything connected. And so that is that. I'm not going to do the CAN wire yet because I don't need it, but that would go there, and so that's fine. All right, so we've measured polarity, we've checked that, and we've confirmed it. And so now we know how to measure voltage and polarity using a meter, which is the obvious part. You set it to voltage, you've got the probes going on, that's fine. We're going to do that again with the voltage of the battery pack when we get this hooked up to the computer, but we need to also set up the way to measure current on this. And now multimeters can measure current if they are placed in line, meaning in series with the circuit, and your particular meter should have instructions on how to do that. If it doesn't have that function, you should very much get a meter that does. And this is not something I normally do because, as I mentioned, I use the power supply over there, which has the instrument panel for measuring current. It displays the current that I set, so you could set it, and that's fine. That power supply is not particularly expensive in the context of lab equipment, and so I think it's a good investment if you're going to work on this stuff, either just for yourself or with your community or whatever the case may be. But if that is not a possibility for you, you can indeed just measure current with a multimeter. Usually the ports that you're using on the meter are different, so these two on the right, the input and the common, are what you would attach the regular probes to for measuring voltage, resistance, things like that. This has another one because each of these are fused. So there are fuses on here. The A on the left for measuring amps is fused at 10 amps, and so if more than 10 amps flows through the meter, it will blow the fuse to save the meter, and it will cut the circuit, and then it'll stop flowing. So what I'm using for that, these are commonly available. These are some wires with the little banana plug barrel thingies that go into the meter and alligator clips, and we are going to use the convenience of this open wiring for the charge adapter to be able to do that. So we're going to cut this and splice this in. I'll show you in a second. So this would go into that plug, and this would go into this plug, and the way it works is this becomes part of the circuit. So this is going to sit in here, and current's going to flow in here and out there, and it's going to measure it. So we're going to do this on the positive side, and I hate doing this. You cut it, and this is 16 gauge, and you strip it, and you strip that. And by the way, I hope it's obvious that this is not plugged in, but you don't do this to live wires. Because again, constantly surprised. And so the charge source is going to come in from here, because this is the part that's going to be plugged into the charger. And so this is not actually how electrons flow, but we perceive it, I perceive it, that it's going to come in from there and go there. So this is where it's coming from, and that's where it's going. And so where it's coming from is going into the 10 amp fused port, and that is going to be clipped right there. And an alligator clip to some 16 gauge wire is secure enough to handle the 4 amps of that charger. Since the current is not that high, this kind of connection is decent, especially for temporary use. And so now you can see that on the positive end, coming from the charger, it's going to flow through these wires into the meter here, and then out of the meter there, and then into there. Now, this is not new stuff. You can find videos on how to measure current with a multimeter all over YouTube. All over YouTube. So if you've never done this, you need to be damn sure you know what you're doing and that your wiring is right before you do this. Again, educate yourself. Do that. Watch those videos before you attempt any of this crap. Now, these connections are good. I'm content. I will insulate them as well. I like using the green rough surface masking tape because it's very sticky, and it also is not as gross to remove as electrical tape, and it's a little bit less finicky than Kapton tape. And so for temporary stuff that I need to insulate, like some alligator clips, it works. A couple turns of that. Make sure there's no more exposed clippage or wireage, and I'm content with that level of insulation as it sits here on the bench. And so, yeah, plug the charger in, and we'll be good to go. Okay then. And so that is essentially how it will go. This is just the regular charger line with the adapter to plug into the charge port, but sitting right there in the circuit in line is the fused multimeter that we will use to measure the current. All right, now we've got set up with the computer, battery, BMS, meter. The charge adapter stuff that we just modified to measure current, we're gonna set that aside. We're not gonna do that first. So we're gonna unplug that whole thing from the meter, set it aside. We're going to get the original just voltage and other stuff measuring probes back into the meter where they belong in the proper input, because we're only gonna be measuring voltage, and that's the first thing we're gonna do. So I'm gonna take the probe covers off. That's what I'm going to do, because I'm going to measure voltage directly from the battery, which is this discharge port. And so I will be able to measure the voltage directly. And just to demonstrate that, set this to the voltage setting, voltage DC, and I will add this probe to the negative, this probe to the positive, and it will read 73.1 volts. And so that is the actual voltage of this particular battery. So that's somewhere sitting, I don't know, 40-ish%, something like that. So that is what we're gonna do. We're gonna be using the voltage measurement. And so we're going to get our reliable, which is over here, USB-C cable. And by the way, this is a V1 XLITE, and the USB port is a point of weirdness and failure, which is why the V2 has no USB port, but this is not about that. And so we will now plug in the USB port to the BMS, and it should wake up. All right, you hear the good detection sound. And the connections with these, as they are with VESCs of all sorts, can be spotty. So sometimes you might have to have it at an angle, you might need to jiggle it, whatever the case may be, and be sure that there's not nothing falling on there and shorten it. And sometimes this port doesn't work. You might need a different port. You might need to reboot your computer, restart the app, whatever. If you're lucky, it'll just straight up work. So you hear the stuff start, and we'll hit connect, and I already get an error because fucking great. Let's try this again. Yay! So I flipped the USB-C port or cable plug around, so I just turned it over and then used a different USB port, and now it connected. So there you go. That proves my point. So now that we're connected, the very first thing we're going to do is go over some of the basic stuff. And we are going to, the firmware on this should be updated, and so we're not going to touch that. Make sure that you, up here on the right, there's a thing that says read BMS configuration. Make sure that you've read it, and that way the settings that are here are appropriate. And so down here on the left, there's a thing called settings, and we click there, and really you just go through the obvious parts. And so under general, power state, nothing here you really need to change. The defaults are fine. The limits, what I do is under the limits tab right there, maximum charge current allowed. I set this to 10 amps. By default, it's 100 amps. Not that it really matters because you wouldn't charge such a pack at 10 amps or more, but in the event that the charger for some reason has some weirdness with the current control potentiometer inside it, and this thing just shoots up to like 12 amps, and the wiring in this particular setup can handle it, but 10 amps or 12 amps is not really good for the cells, because the Molicel P28A, I think the think the charge max for it is 4 amps per cell. Anyway, I set it at 10. That's what I did. The rest of it I leave alone. Can the default settings work? And sensors, there's nothing in there to change. And so that stuff I will save. And to save, on the right, there's a write BMS configuration. So you click that. And then right below it is a floppy disk, store BMS configuration to flash. Do that. That writes it to the flash memory on the BMS so that it stays on after it powers down, or the settings stay there after it powers down. Now here's some of the important stuff. Cell management. Specifications of the battery and the BMS. Pack configuration. Cell monitor type, leave it alone. Cell monitor count, that's how many of the integrated circuits are monitoring it. There are 2. It says 2. We leave that alone. All right. Parallel modules count, 1. Leave it alone. Cells in series. This says 15. I think it's because I was using this one to try and rebalance a CBXR, which is a standard 63 volt 15S battery. So we're going to change this to 20. Cells in parallel. This particular pack has 2 because it's a 2P. So we're going to change that to 2. Battery capacity total. The way you get that is you take the battery capacity of a cell and multiply it by how many cells are in parallel. So the P28A has 2.8 amp hours of capacity, and this is a 2P, so we double that, which is 5.6 amp hours capacity. All right, and now we go under cell specifications. Lithium ion, cell hard undervoltage, 2.5 volts, hard cell overvoltage, and cell soft overvoltage. So that's what relates to charging. The defaults are the soft overvoltage, which is where the charge throttling starts to happen, where it dials it back, is default to, you can actually click the default here. Oh, I guess it didn't change. The default is usually 4.15 volts. Hopefully you know by now that 4.2 volts for any lithium ion cell is full, right? Now, of course, there's wiggle room within the hundredths of a volt. And so 4.25 technically is also full. If you're looking for pack longevity, then what I would do, and also just peace of mind and safety, I would set the cell hard over voltage to 4.20 and the cell soft over voltage to 4.15. That's what I would set it at. If you want to make sure that your cells charge fully all the way to 4.2 volts, or as close to that as possible, because some cells simply don't charge to 4.2 volts, you can set that to how it was before, where the soft overvoltage is 4.20 and the hard overvoltage is 4.25. You're honestly not getting all that much benefit from having it that high or having it at that point. Are you going to get any extra actual range out of it? I don't know, probably not. And so I'm just going to leave it at the default of 4.15 and 4.20. And so we'll go over to the balancing tab. Cell balance start voltage. I believe the default was 4.1. I have it at 4.0. And the cell balance difference threshold here, I think the default was 0.015 volts, which is 15 millivolts. And scratch that. I believe the default was 10 millivolts or 0.010 volts. I upped it to 0.015 or 15 millivolts. That's more realistic as the pack ages. To be perfectly frank, a brand new pack charged to full on this will really only have a delta of like 5-6 millivolts, which is pretty great. And halfway down at nominal voltage, it's even less. And so if you're sitting there and this thing is like 6-8 months old and you're trying to get a tiny difference threshold, it's just going to keep running and balancing and generating heat, when really in effect a balance of 0.02 volts is damn near inconsequential when it comes to how much of this battery you're going to actually charge to and use. And so there's that. You can leave it at default if you want. I leave it at 0.15 volts, and that's I think is fine. Cell balance all the time. Default is false. Leave it. You don't want it balancing all the time. There's no point. All right, discharge doesn't matter. This stuff, the throttling doesn't matter because it has to do with a specific type of charger that's not being used here today. SOC is state of charge, that's percentage, so state of charge percentage. This looks at state of charge, and the default is Coulomb counting. I set it to Coulomb counting and cell voltage lookup, and then the rest I leave alone. So now that these are done, write BMS configuration, go below that to the floppy disk, and write to flash, and that's good. And now we're going to go down to switch. Discharge doesn't matter because it's a charge-only BMS. Charge. The charger enable threshold by default is set to 0.5, that's half an amp, and it has to have a sustained current flow of half an amp to stay charging. That's a little bit high, and so I set it to the minimum that it will allow, 0.05 amps. So when this enters into the constant voltage phase of the charge and the charge rate slows down, if you want to leave it for a little bit to balance, then it will time out if it's too high, because a regular wall charger green lights at 1/3 of an amp, usually, more or less. There's variation, of course, and so I would prefer this BMS to cut the charging based on cell voltages that it detects rather than a low current from the charger. So that I leave at 0.05 amps, and the rest I leave as is. And so I will write BMS configuration again, and then below it the floppy disk, store BMS configuration to flash. Now we're going to go down to the tricky stuff that is really just a matter of measuring and display work. But before we get to that, we're going to go on the right. Down below the floppy disk is RT and a little graph. That's stream real-time data. We turn that on so it's green. That way we get the information it's reading off of the battery pack. So we go down to the left, data analysis, real-time data, and you'll see graphs. You have information on the bottom. If you go to the leftmost tab, cells voltage, it will show you, assuming you wrote the proper amount of cells. So this is a 20S battery, which now is reading that we've set it to 20 cells. It's reading the 20 groups, and you see them that they're pretty much dead even. It gives you individual cell voltages. So each of the parallel groups in this pack, the actual voltage detection of the individual groups on every ENNOID XLITE I've seen and handled and used is pretty much dead on. So if this says that the groups are at 3.646 volts or 3.647 volts, that's pretty much dead accurate from everything I've seen, as far as I have seen. The stuff that needs to be adjusted though is over here on the left, VPAC, which is the voltage of the entire pack. That is also important for it to read properly. The IPAC, which is the current. And over on the right, voltage load and voltage charger. So the voltage load you don't really adjust. Voltage charger you have to adjust. And so those are the things that we're going to worry about. SOC says that it is 100%. That's obviously wrong. And this BMS has been connected to different batteries. Once it's connected to the same battery and it's run through charge cycles, it usually adjusts this pretty well. Like it matches up and then it starts to adjust the state of charge. And so that's that. Right now, if you look on the bottom right, it says fault state, max OVP, UVP. So this is in a fault state because it was set to 15S, and that's the wrong voltage for the pack. And so it is currently in a fault state. So that will be cleared before we do anything else. But since we're not actually changing any operational states, we're just checking right now voltage of the pack. And so the voltage of the pack, using our regular old meter, it makes that when it's been on for long. I'm going to set that here so it doesn't press anything. We're going to measure the voltage of the pack at the XT90 discharge connector, and the voltage of the pack is still 73.1 volts. Now, the voltage of the pack, in this case, is fairly accurate. And that's right there, 73. You see it kind of fluctuates because reasons. And right there, 73 point, it hits 1. It sort of just fluctuates, but it more or less averages to 73.1. And that is fine. If this is way off, right? So this might read, who knows, 85 volts, 60 volts. If you're certain that your pack, by measuring with a meter, is at this voltage, 73.1, then you need to change this following area. You go to, on the left, under Settings, Signals, and right here, you have a number of settings called factors. These are what you need to change. And so, the first thing you want to change is under pack voltage. Pack voltage factor is the one you want to change. Right now, I have it set to 2.483300. I arrived at that one essentially by trial and error. And so on a different one, let's see where I had that. Yeah, that's fairly different. This is a value that I got for a different BMS. That was 2.486. And so it's slightly different from this. And the default value, I think it was 2.5? Maybe, yeah, it was probably a bit high. So really what I did was I went to the lower ends of this decimal point into the thousandths and just moved it up and down until it trued up. So if we change this to 2.5 and we write it and we go to the real-time data and we look at pack voltage again, you'll actually see that the pack voltage is reading at 73.5, 73.6, which is high. If we make this very low, 2.2, and we save that and we go back there, it'll read the pack voltage as 64.7. So that is how you adjust it. You'll see that such a difference, changing the tenths of decimal points, will have such an impact. We again know that this battery is at 73.1 volts, and so we will return it back to 2.4833, because I think that's what it was. And so this is kind of like a trial and error because there are tolerances for certain detection chips. And so 2.48-ish is where I found most of them to work. And so, yeah, 73.1-ish. All right, so it's hovering there. And since the cell group voltage detection is pretty spot on, as far as I've seen, you get this kind of in the ballpark. It's always going to fluctuate. That's just how the detection for it goes. And so that's the pack voltage factor, and that's how it's going to go. And so once you have that, the pack voltage factor and all the other stuff just for the specs of the actual battery, once that's there, make sure that you have written it and you've saved it to flash. And then what I like to do, because it's still in a fault state, because it was previously, wrong and then we fixed it, I like to disconnect it and then unplug the USB from the computer, because the USB power keeps the BMS awake. And so for it to reset out of a fault state, it's got to go back to sleep or power itself down. And so once it powers itself down, by the way, it should power itself down. It should power itself down. If it doesn't power itself down, that's bad. That's defective and you need to deal with that. But it should power itself down. And so we're going to assume that it powered itself down, which it did. And so now we are going to plug it right back in. And it should wake itself back up. Give it a second, and then we will go to, there's a button on the right to connect it, all the way on the top. And it's now connected, and the real-time data is still clicked, and we are streaming the data, and the pack voltage is fine. And now it says system OK on the bottom right, and there's no more fault state, because 20S battery, parameters were set right, and so it is as it is expected to be. Now, we have to set the voltage of the charger, and we know that this charger that we're using, this wall charger, does have a setting of exactly 84 volts, but when you plug in a charger to a battery or a charge port where the battery is lower, what happens is the actual charger measurement lowers, because that is the voltage being applied as it is in the constant current phase. And so V charger, when you plug it in to charge and the battery's not full, is not going to read the 84 volts. And so unless you have a power supply where you can read the current charge level, so unless you have a power supply that shows you the actual voltage during the charge, it's going to be kind of hard to deal with. And so if you don't have access to that, the next thing to do is when you plug it into charge, you look at the voltage of the charger versus the voltage of the pack, and the voltage of the charger should be slightly higher. Now, it was recommended by Kevin for an ENNOID to set the charger voltage factor a little bit higher to make sure that the voltage of the charger being detected is always slightly higher than the voltage of the pack. That will always make sure that while it is needing charge, it will stay in the charging op state. And so that is something to consider. What we're going to do is now plug in the charger. And by the way, I do have, since we made that modification earlier, I do have it hooked up to the meter set on current. And so it's going to measure the amperage of the charger. And so this is going to be set up for measuring the current and setting the current setting on here. We're not going to do that right now. It's just that since we already modified that charge adapter for the XLR plug, it has to go through here because otherwise it's not going to work. And so this is set to DC amps, and it is going to measure it anyway. And so we'll have that information on the meter. We're just not going to plug it in right this second to the settings. We're just going to check out the charging voltage and make sure that's correct. And so we're going to plug in the XLR as per we expected to earlier. And so it is connected. It should now enter the charging op state. Wait. All right. By the way, before we do that, if you do plug in the charger and it begins charging and you unplug it, what will happen is, like before, the BMS will stay awake when it's connected via USB. So if it's staying awake and it's powering down, like it says power down, you just have to disconnect it from ENNOID tool and then unplug the computer USB, wait for the ENNOID to shut off, power down, the lights go off, then plug it back into the computer, connect it, and then you should be able to enter in the charge state. Obviously, when there's no USB, because everything's done and closed up, that won't be an issue because it will put itself to sleep, but the power from the USB port does keep it awake. And so that's something to keep in mind as you're going through configuring. So right now it is reconnected. We are ready to plug in the charger, and all right, and so now the op state switches to charging. The red light on the charger and the fan turn on, so that's great. And the meter is reading, so it is measuring currents. All right, so it's actually measuring 3.80 something, and it's kind of climbing. All right, so that's probably going to even out as it gets where it's going to go. But right now we're a hair under 4 amps, which is fine. This doesn't have to be super, super, super accurate down to the milliamp. But point is that it is now charging, and that is good. And so we see that. What we're going to take a look at first is the voltage of the charger, which is 74.5-ish volts. And so that is almost dead on with the voltage of the pack, if not a hair higher, like just barely. And so if that's way off, the one you want is under charger voltage factor. Now, for this particular BMS, I did not have to adjust that, and it functions fine all the way up to full, but if you need to, I'd probably start here, let's say like 41.5, I guess, and we'll write that and see if it does anything. All right, and so, okay, so now that 41.5 brought it up to detecting just a hair under 76 volts, and so I'd probably, if you really wanted to keep it above the voltage of the pack, right down, so maybe do like a 41.2 for charger voltage factor, right that, and now it's at, all right, so it's fluttering at around 75-ish. Meanwhile, the voltage of the pack is 74.67-ish. All right, so that's slightly higher. That's fine. Honestly, probably could have left it alone as it is. And so that's up to you. It's really, it's really going to judge whether or not it stops charging based on cell voltage. And so that's fine. You know, it's really about, as far as what it will let the battery do, about cell voltage and the voltage of the pack. So if it's in terms of having over voltage protection, it will measure it from the pack, not necessarily that this is, you know, too high. It's what it's detecting from the battery. So we're going to write that to flash with the floppy disk icon. We're going to leave that alone, and so that's probably fine. All right, and so now we are going to do the current measuring, and that setting is the first one, the discharge current, which really is the same as the charge current, but it's this one, the shunt LC factor. So the shunt LC factor, I forgot what the actual default thing is. And I mean, if you look at your real-time data, right, you want to look at IPAC, and it should have an amperage rating. And if the meter is showing so this is showing 3.949, so about 3.95, just a hair under 4 amps. If that's what it's showing, and this is showing 3.7-ish amps, that is enough that, or rather that's close enough that the function of the BMS is not going to be affected, because this is far over the threshold of 0.05 amps. And, you know, of course there might be some weirdness as it nears full voltage, and so the current slows. And so it's probably a good idea to try to true this value up as much as possible. Since we're here, what we are going to do is go to signals, and I forgot what the value to start was. It might have been 0.0015, I think. This is what I have it here. It's set at 0.001610, and the meter is reading 3954. And so this is, the meter's reading a little bit higher. And so we're going to try, it's at 00161, so let's try 1710, 0.001710. We'll write that, and then we'll go back to real-time data, and now it is reading just a hair above 4. So we're actually a bit closer than I thought we'd get with that. So we're going to drop this down to, we're not going to change that 7. What if we drop it down to 0.00170, and we'll write that. Let's see. And actually, wow, that's not bad. So we got a little bit lower. Let's do 0.0017. Let's go 0.00167. Let's see what that looks like. All right, we write that, go back to real-time data, and it says IPAC 3. It's kind of hovering, I'd say averaging at 3.9. So we could stand to go a little bit higher. 0.00168. Let's try that. Okay, write that, check the real-time data. We are now at 3. All right, so it's hovering. You can see it hits 4, but then it drops down below. So I'd say that's trued up. Because you see how it fluctuates? It goes down to like a 3.85, but then it goes above a 4. And so between that, as far as the median's concerned, I'd say that's pretty darn close. If you really wanted to spend some time with it and get it trued up to the milliamp, you could do that, but it fluctuates to the point where I'm not sure that it's worth it. And so I'd say that's pretty close to what's being detected, a hair under 4 amps, which actually is impressive. Sometimes I get 4 amp chargers that read 3.5 amps, 3 amps. You know, they're all over the place. And so I'm content with that. So we will write that and then save it to flash with the floppy disk icon. And it's still charging and it's running, and you can see the voltages of the cells are rising, and it seems all right. The voltage of the pack is rising as it should. You'll notice that it actually has, so here on the left side, you've got high, low, and average. That's the spread. So the highest voltage it detects from the cells. My meter gets angry when you don't turn it off. Like, you leave it on, it just beeps at you. It used to scare me because I'm like, what the hell is beeping? Anyway, so you got high, low, and average. You've got the lowest cell is reading at 3.808 volts. Highest cell is 3.816-ish. And so the mismatch, that's the difference, that's the spread, is like 6 to 7 millivolts, which is fantastic, which makes sense because that's a new battery. I just made it. And you make a new battery with fresh cells that were stored well, you're not going to have a massive spread. That happens, you know, stuff that's stored in really, really hot environments, stuff that gets like frozen and thawed a million times, you know, or if it's you know, really, really driven heavy, maybe a year from now it starts to wear and the cells wear differently, and so the spread starts to, you know, widen. But for a new pack with fresh cells, that's to be expected. This is good. So this is a good situation, and it's still charging. You can hear the fan. That's great. And so now that the BMS is set up and you've saved and we've written it to flash, what we'll do is, what I'll do is I will disconnect the charger. So we'll do that. So we'll unplug that from the XLR port, and that's fine. And cool, so the charger now is disconnected. And of course, let's zoom out. The BMS is still awake. See those green lights? Because it's still connected to the USB. And so the USB power keeps it awake. So we're going to disconnect it. Make sure it says it's disconnected. We will disconnect the USB. And it goes back to sleep, or it shuts down. And then we very carefully remove the USB. And then this is configured. And so you can, of course, unplug it. What I would do first is unplug the balance wiring, and then, actually no, what I would do first is disconnect the charge port, which is this, carefully. So that's the charge port, which had nothing to do with it power-wise anyway, currently, because it's unplugged. And then what I would do is disconnect the balance wiring, starting from the higher up one, which is the small one, then the larger one, which goes all the way down to the first cells. Then I would do the pack terminal. And so now this is disconnected, but since we wrote everything to flash, it is saved to the memory of the BMS, and so this is configured. And so if I connect this back to this battery, the settings will be there, and it will be appropriate for use with this battery and this charger, and it should just work as it does. So now that that's been set up, I can actually do the final wiring in this box before I close it up, which again, if you're using the CAN connectivity to connect the BMS to the VESC, you want to connect the CAN connector absolutely last. So the battery connecting to the other XT90 for the discharge has nothing to do with the BMS because it's direct. But what I would do is then place this, and that's going to be documented how I do it in a separate video and article, but I would place this as I deem appropriate for the space, make sure clearance, wiring is managed decently, secure, adhere, however it goes down, plug all the power stuff in as we did just now, then plug in CAN last, and then once everything is secure and clear and good to go for rugged use, then you would have a full assembly because the Molex is still connected in the front, and that way you won't have any weird things where, you know, your grounding is off and then your CAN chip gets burned out and then this thing breaks. So Molex is connected. Everything in here should be connected and secured. CAN gets connected last. Then once you make sure everything is secure, close it on up and you have that front and back enclosure assembly ready to install into the frame. So I don't know how long this video is going to be. Might be an hour. Who the hell knows? If you made it through, thank you. I really hope this was helpful. And go with God, and yeah, good luck.